Alright, hi y'all. Today we're going to be doing this three-phase circuit problem. This comes from a past exam for circuits and systems, and I just wanted to introduce you all to this three-phase circuit problem. Now, first thing to look at, or a lot of the times when you're doing these three-phase circuit problems, you almost always want to get into the A phase, which is the single phase equivalent. And that's what we're going to be doing in this problem here. So we're told that a balanced three-phase line has an impedance of 0.5 plus J4 ohms per phase. So we can say this is ZL, Z line. Now the line feeds two parallel balanced three-phased loads. Okay, that's very important to know. They're in parallel. What do we know about parallel? Well, we know that the voltage across the lines are going to be the same. So VAB for load 1, we can say like load 1 is equal to VAB, if y'all can see here, VAB for load 2, because they're on the same nodes or same lines. And whenever I draw this, it'll make more sense. The first load absorbs 691.2 kilowatts and negative 201.6 kVR. See how this light turns off. This might be okay. Let me redraw this here. I don't know if that's any good. Hold on, sorry guys. That might be better. I can't really print right now, so I just want to get this video done. So here we notice we have a real part and we have an imaginary part of our complex power. Okay, well that's very important to know. Let's write that down. So S1 is equal to what? S1 is equal to 691.2 minus J 201.6. This is in kVA, kilovolt amps. Very important to know. Now the second load is delta connected and has an impedance of 622.08 plus J181.44 ohms per phase. Okay, per phase. Remember that is each phase has this much impedance. Now the line to neutral voltage at the load is 7200 volt RMS. Okay, anytime they say volts in these kinds of questions, they usually mean RMS because we're using three-phase circuits. So even if he didn't say RMS, we would take it to be RMS. And the question asks you to find the magnitude of the line voltage at the source end of the transmission line. Okay, so there's a lot of terminology we have to be comfortable with. Source end, transmission line, line impedance, delta connected, line to neutral, line to line. These are all important terminology to know. Now let's draw this three-phase circuit. So it doesn't give us anything about the source side. So what we can do is we can just draw a box. Now why draw a box? Well, we don't care what's on the left side. We will eventually, but we have to find the line voltage. So we'll say this is source. Now what is the line voltage? Well, the line voltage is the voltage or the potential difference across the lines, across two different lines. Now we know it's balanced, so we know the source of voltage will be the same magnitude but different phase by 120 degrees. So just for our analogy here, we're only going to deal with the A and B phase. So A minus, this is small a, small b. This is what they give us. Or this is should be what we want to know. To find the magnitude of the line voltage VAB, at the source end of the transmission line. This is what we want to find. The source end of the transmission line and the line voltage. Now, we know each line has half a volt or half ohms plus J4 ohms. So we can write resistor in series with an inductor. So this is 0.5 ohms. J4 ohms, same thing for this one here, same thing for this one here. They all have the same values because it is a balanced three-phase circuit. Now these are the transmission lines, and now we can go to the load. Well, first of all, we're only given the first load is in parallel with the second load, and we're only given the power, the complex power. So what we're going to do is we're not going to deal with the components inside of this. Let's just draw another box of S1. And we'll say this is, what was it, 691.2 minus J201.6 kVA. I'm only going to draw this here because we don't have the components. We don't need to solve for them in this case. But we know it's also in parallel, so we need to redraw here these three transmission lines. And it says we have an impedance of, and it's delta connected, 622.08 plus J181.04. This is per phase, and it is in delta connected. So what we're going to have here is we're going to have a resistor series with an inductor, then in another resistor in series with this conductor. Then we have this in resistor in series with this inductor. This looks pretty bad, but that's what we have here. And each one of them, since I didn't leave myself enough space, 622.08 plus J181.44 ohms. Each of them will go to these phases. Now it says the line to neutral at the load is 7200 volts. Well, when we're dealing with this, when we're labeling this, why did I put little a little b here? Well, little a little b is the connection from the source to the line. So we have A, B, and C. After the load, we have capital A, capital B, capital C. And at the source, we have like little n over here and big N over here. Or I guess big N would be right here. This is not too important for this type of problem. It is important that you know how to label these three-phase circuits, because on like any type of diagram, they will have some labels like this. It's important for us to know, because when we're dealing with line to neutral, we're dealing with an A value to an N value. So if it says the voltage, line to neutral voltage, we're dealing with the line and we're dealing with the N. If it's on the source side, we deal with little a and little n. But remember at the very beginning, I want to get this in single phase. Well, what does that mean? Well, I only want to deal with the A phase for now. So we only want to deal with A phase because that is our reference phase. I'm going to assume we are in positive phase sequence. So we're in PPS here, positive phase sequence, which is ABC. So we let A be our reference. B is angle negative 120, and C is positive angle 120. You don't need to know this if you're in class with Hebert. He just gives you a massive crib sheet, basically, which you can do almost any single problem on it. But you do need to know the terminology, because he doesn't tell you what the terminology is on the cheat sheet, of course. Now we're in the A phase. What the single phase essentially tells us is we want to find the voltage or voltage across the source and the load and the current through the line for a single phase. So what we're going to draw here is we're going to draw our source, because again, we don't care what the source is. Now what we have here is we have the transmission line, we have a resistor, and we have an inductor, which is our I guess you could say transmission impedance right there, right? Our line impedance. And then what do we know? This is labeled capital A, this is labeled little a. And we have a load, one load, connected in parallel with another load, right? And this will come all the way over here, and look, we have a complete loop. Now what was this? Half an ohm and J4 ohms, and we can label the current here I from little a to big A, which is essentially going to be this big loop. Then we have little n here, and we have capital N here. So what do we know? Well, we know the phase voltage at the load is this. And we know the phase voltage at the source is this. Now, what does this box represent? This box represents one of the loads, which is our S1. But is S1, or S total, equal to the A phase complex power? Well, it won't be, because whenever we're dealing with this big S1, we're dealing with 3 different lines. When we're dealing with an A phase, we're only dealing with 1. So a very easy way to think about this is S1 is equal to 3 times S1A, the A phase of that first load. So how can we get S1A by itself? We divide by 3. So S1A, which is the complex power absorbed for the A phase for this first load, is equal to the total complex power absorbed by the first load divided by 3. And from that, we should get 691 point, what is it, 2 minus 201.6i divided by 3. And what we get is 230.4 minus J67.2. And this is in what? kVA, kilovolt amps, still. Okay, so this is right here. This goes right here. But what about this? What do we do with this load? This is our second load, right? Second load. What do we do with this? Well, we know the first load was given to us in power, complex power. This makes it very easy for us. Second load is given to us in an impedance that is in delta connection. When we do the single phase equivalent, we have to make sure this is in Y connection. So there is something that we should know here. The delta connected load, we'll call it Z delta 2, is equal to what? How do we go from delta in positive phase sequence, from delta to a Y configured load? Well, when we want to go from delta to Y, we do Zy of 2 is equal to 1/3 Z delta 2, which is going to be equal to 1/3 times our delta impedance here, or delta load impedance, which is 622.08 plus J 181.44. And with that, we should get 207.4 plus J 60.48 ohms. So then this goes here, this is the resistance, and this is the inductance. I hope y'all can see how we got from delta to Y here. We divided by 3. And now we have the impedance here, we have the complex power here, we have the current labeled through this line here, and we have the voltage, the phase voltage at the source and the phase voltage at the load. What do we do now? What are we trying to find? Why did I even do this? Well, something that we want to find is we want to find the magnitude of the line voltage at the source end of the transmission line. So if we go to our phase, A phase, source end of the transmission line, this is the source end. We want to find the line voltage. Okay, VAN, this is the phase voltage. To go from phase to line, we have to multiply by √3 and angle 30 degrees. So we need this somehow. Let's create an equation based on our A phase to get this. What do we know? We know if we create a KVL, we know VAN is equal to, this is equal to the voltage drop across our line, which is our current times our impedance here. Sorry if you can't see this. Half plus J4 plus VAN, the voltage across AN. What is the voltage across AN? Up here it says that the line to neutral, or our phase voltage, at the load is 7200 volts RMS. Oh my gosh, VAN, that's 7200. VRMS. We already know this, so what don't we know? We don't know this current. Okay, well, how do we find the current? Well, we can do a KCL. What if we do here? What if we do this? Find KCL. We know the current going through node A. Here, well, let's create a node here. We'll call this node A. We have to find the current flowing through here, and we have to find the current flowing through here. Add these up. This should be equal to this IA, the line current. All right. Hopefully y'all got all this. If you need to pause and make sure to comment if there's a question you have about this and why I'm going about all this business. There might be a faster way, but this is the way Dr. Hebert taught us, so this is the way I'm going to do it. So we go to three-phase circuit, then we go to A-phase, make it easier for us to solve these values, and then we transfer it back into the three-phase. If you want to think about it as time domain versus phasor domain, you can. So let me redraw this here. Let me redraw this equation, or rewrite it here. We have VAN is equal to IAA times half ohm plus J4 ohms plus 7200. I'll leave this as 7200. We need to find IAA. Well, IAA is equal to, let's bring this other paper back. This is equal to the current through here, which we'll call IS1A, and then this other current going down through here, and this load IS2A. So IAA is equal to IS1A plus IS2A. Let's write that down here. IS1A plus IS2A. All right. How do we solve them? Well, looking back at our single phase, what do we know? We know the complex power of this load. We know the voltage across it. Well, this is very easy. We know the power, we know the voltage. How do we find the current? Well, we'll use one of the equations here. We know complex power of a single phase S1A. What do we know? S1A is equal to the voltage across the load times the conjugate of the current through, which is IS1A. Sorry, IS1A conjugate. So we can rewrite this. IS1A, we get IS1A by itself, is equal to S1A divided by the voltage across the load. Load 1 at least. Conjugate. So then what we get is IS1A is equal to S1A, which was, what was S1A? 230.4 minus J67.2. Remember, this is in kVA, divided by the voltage across it, which, what did we get? 7200. Remember, this was what was given to us, and this is in volts. Something we have to notice here, we're going to get, volts are going to cancel, we're left with kiloamps. So we're probably going to have to do something here, we're going to have to change kiloamps to amps. And don't forget this conjugate. When we do this, we get 0.032 plus J 9.33 times 10 to the negative third. Remember, kiloamps. To go from kiloamps to amps, we multiply by 1000 and we end up getting 32 plus J 9.33. This is in amps. Okay, well, we have IS1. IS1A is very easy. Use the complex power, you divide by this voltage across it, and make sure to take the conjugate. Alright, we find IS1A. What about IS2A? Let's look back here. IS2A. Well, IS2A, we know that we're trying to find the current through here. We know the impedance of this load. We also know the voltage across it. This is the same node. So we can just do a very easy Ohm's law. Voltage divided by our impedance to get the current. No conjugate needed. So, what do we know? We know Ohm's law. VAN is equal to IS2A times the impedance of load 2. I don't know how I labeled it before, but I'm going to say Z load 2. So then we rearrange this, we get IS2A is equal to the voltage across the load divided by ZL2. Plugging in the values, we know VAN to be, what, 7200? Divided by, and this is in volts, divided by the load impedance, which is 207.4. I guess I should put a Y here. We have to be careful because before we had it in delta, we want it to be in Y in this case because we're in the A phase. Plus J 60.48, and this is in ohms. Volts divided by ohms gets us amps. And now we're left with 32 minus J 9.33 amps. Perfect. We have IS1 and IS2. Hopefully y'all followed this. This is very, I would say, simple complex power calculations. The hard part in this is transferring three-phase to A-phase and understanding what this means. Alright, so we know IS1, IS2. Remember, IAA is what we're trying to find. IAA is equal to IS1A minus, or plus, sorry, IS2A. Well, what do we have? We have 32 plus J 9.33 plus 32 minus J 9.33. Wow. Well, the imaginary parts, they cancel. 32 plus 32 is 64 plus J0 amps. So the current through the line is 64 amps. Okay, well, we need to go back. We need to use the other equation because we're trying to find the voltage at the source. The line voltage at the source. This is the phase voltage. So let's find the phase voltage at the source first and convert it to line voltage. So remember this equation, we have 7200. All we needed was IAA, which we have now. So actually, I'm just going to do it on this paper here. This is now equal to IAA, which was 64 plus J0 times 0.5 plus J4 plus 7200. And what we get with this is 7,232 plus J 256 volts. All right, this is our phase voltage. This is equal to VAN, and this is at the source. We know it's at the source because it's little a, little n. Okay, well, we want the line voltage. How do we go from phase to line in a positive phase sequence? In a positive phase sequence, we do phase to line by doing the line voltage, not the line voltage, sorry. Yeah, the line voltage at the source, sorry, this is at the source, right, source end, so this is little a, little b, is equal to square root of 3, angle 30 degrees, times the phase voltage at the source. So what we're going to get here is we will end up getting 10,626.3 plus 6,647.1. And remember, this is in volts. All right. So this is mostly our answer. This is in the rectangular form of our line voltage at the source end. It's asking for the magnitude. So essentially what you do is you take the square root and square them both. What we end up getting is the magnitude of the line voltage at the source is equal to 12,534 volts or 12.534 kilovolts. And that's what I get. So hopefully y'all can see where I got all of this work from. I'll zoom out here. First thing we did was we made this drawing in the three-phase just so we could get a little bit of a better understanding of what this is. And then we went into the A phase, we went into the single phase to find that phase voltage, because we know we can easily change from phase voltage to line voltage, but it's hard to analyze this three-phase just straight out of the gate, especially when you have this. It's very difficult. And then what we did here, all this page was the current, the line current through the A phase. Now, if you notice, the line current through the A phase in the A phase circuit is the same one as the line current through the three-phase circuit. In a balanced three-phase circuit, by the way. Now, what does this mean? Does this make sense? Does this answer make sense? We have the magnitude, or we can even think the magnitude of this is 12,534 volts. So this is here. That's here in this three-phase. Let me zoom back in. This is here in this three-phase. That means the voltage across here is equal to the line current times this, the voltage drop across this, plus the AB, the big AV voltage, the line voltage at the load, plus this other current going through this, the line current IBB, and the voltage across this line. Actually, it would be the addition because the current is going in the opposite direction. And this is what this is equal to. Alright, so hopefully this was okay. This is what I got as the answer at the very end. Magnitude is 12.53 kilovolts. And hopefully this made sense. If anyone has any questions, please send them. Because, I mean, this is the first time I'm doing a circuit and systems problem with three-phase. As like kind of teaching. But for the most part, this is how he does it. All he does is take the three-phase, change it to an A-phase, solve for any variables we need, change it back into three-phase, and we usually have the answer. But, alright. Hopefully y'all understood here, and please let me know if you want a specific problem done. Please send it to me, and I'll have it done pretty soon, I would think. Depends on how busy I am, but thank you for joining.